Hi guys, welcome to my world of physics infinity. In this video, we are going to once again have a look at the problem of the rolling disk and consolidate your concepts of dynamics of rolling. I create a new situation where there is a uniform disk of mass m and radius r, and it is spun anti-clockwise with an angular velocity omega naught equal to v naught by 2r, and at t equal to 0 it is given a translational velocity v naught. So v naught is the velocity of the center of mass. If you look at once again the 3 points at t equal to 0, the center of mass has velocity v naught and the point of contact P has velocity v naught plus v naught by 2, because it will be omega naught r add on to this, so that becomes 3 v naught by 2, and the top point A has v naught by 2. Well, A I am not considering right now. My major focus will be on center of mass and the point of contact. So this way, at t equal to 0, it is a case of forward slip, impure roll, and since the point of contact has velocity relative to surface, the surface is at rest, relative velocity with respect to surface forward, therefore kinetic friction at P will act backward to oppose this relative motion. Now once again Fk will play its wonderful role. Fk will try to reduce the velocity, translational velocity v naught. We can use the Newton law of motion to understand that, and Fk creates a torque about an axis through center of mass perpendicular to plane of disk, and that is a clockwise torque, or in other words torque which is an axial vector. The Fk will create the torque that is along minus k cap, clockwise torque about an axis through C perpendicular to the plane of disk. So Fk is doing two things. Number one, it is trying to decrease the translational velocity and is trying to increase the clockwise angular velocity till at the instant t it so happens that the translational velocity v naught becomes v, and the angular velocity, instead of anti-clockwise, because continuously the clockwise torque was acting due to Fk, that becomes omega, look at that, clockwise v upon r. That's very interesting, because if at this instant t velocity center of mass is v and omega r backward is also v, then at the point of contact Vp is 0. Vp 0 means what? Pure rolling has begun. Why? Because Vs is already 0 and if Vp also is 0 forward, both forward, so vector wise now there is no motion of P relative to surface. Well, that is the condition of pure rolling. So pure rolling has begun. Our purpose is now to find the velocity at which the pure roll begins. In this video I am going to, because I have already told you that I am going to make you conceptually very strong, I am going to use 3 methods to calculate V. 3 methods to calculate V. First and the quickest method will be the conservation of angular momentum, principle of conservation of angular momentum, but I can conserve the angular momentum only about an axis passing through P, not through C, because at C, Fk about an axis through C, Fk creates a torque. But if I consider the point P and I take an axis perpendicular to disk, then all the 3 forces mg, n, and of course when pure rolling begins there is no Fk, so there is no force which creates a torque about an axis. So throughout this I can now at the instant t equal to 0 and at the instant t while the Fk was acting, I can conserve the angular momentum about an axis perpendicular to the plane of disk passing through P. Now through P, if I take an axis through P, then for the angular momentum, I'll have to take two parts. The orbital angular momentum, where I take the disk as a... To find velocity at pure roll, once again, we take another method, that is dynamical method. For this, first I consider the motion of C, that is center of mass. For the translational motion, Fk is an opposing force that is creating retardation. Initial velocity, so final velocity V is initial velocity V naught minus, because Fk creates retardation, minus Fk upon m into t. Fk is mu k into mg, mm cancel, so mu naught minus mu k gt, number 1, first equation. Now let me frame the equation for the motion of point of contact. For the motion of point of contact, the point of contact acceleration, in fact retardation, will have two parts, one due to translation and one due to rotation. So if I take that, the motion of the point of contact, the final velocity Vp is 0, the final velocity at pure roll Vp is 0, initial velocity Vp was 3 V naught by 2, well that was 3 V naught by 2, and AP well is retardation, so minus AP into t. Now AP, the retardation part for the translational motion is Fk by m, that is A, that is Fk by m. So I can take that as minus Fk by m, translation, okay. Now for rotation, it will be torque divided by I, moment of inertia, that will give me alpha, then alpha multiplied by r give me the tangential acceleration at p due to torque, and the torque is created by Fk. So here we are. So if I apply that, then torque is Fkr divided by moment of inertia mr square by 2. Well, that will give me alpha, angular acceleration, multiplied by r is the tangential acceleration due to rotation at p. R square cancel, 2 goes up. So total AP retardation AP is 3 Fk by m. Fk by m due to translation and 2 Fk by m I am getting due to rotation, the tangential acceleration. So minus 3 Fk by m is the retardation. Well, I put that in the equation of motion. So 0 is equal to 3 V naught by 2, and I replace AP. So minus 3 mu k gt, that is equation 2. From this I obtain mu k gt as V naught by 2. I put the value of mu k gt in the equation 1. Look at this. So it will be V naught minus V naught by 2, and that gives me the same answer as before, that is V equal to V naught by 2. So two methods we have. By the two methods, principle of angular momentum and also by dynamical method, we are getting the same answer for the velocity at pure roll, that is V equal to V naught by 2. Now I solve the same problem by third method, that is using work energy theorem. I'll use work energy theorem for the translational motion, and then I'll use the work energy theorem for the rotational motion, and then we see how we solve the problem. So first of all, for translational motion, well, work done by Fk is change of kinetic energy. Friction, Fk is doing negative work because Fk acts backward. So minus Fk into x. X is the displacement of the center of mass from the instant t equal to 0 to the instant when it begins to pure roll. So minus Fk into x, change of kinetic energy, half mv, change of translational kinetic energy, half mv square minus half mv naught square. I put x equal to v plus v naught by 2 into t. I get minus Fkt equal to minus Fk times t equal to mass into v minus v naught. I call it equation 1. Keep it. Let's now do for work energy theorem for rotation, for the rotational part. Mind you, for the rotational part, the Fk is creating a torque about an axis through center of mass, and that is a clockwise torque. And eventually it increases the angular velocity of the disk clockwise to v by r in the total time interval t, because this is at t equal to 0, this is at the instant t. So for rotation, Fk r theta, that is the work done if theta is the angular displacement in the time interval t minus 0, that is t. So Fk r into theta should be equal to the change in rotational kinetic energy. Now change in rotational kinetic energy, final minus initial, half, so this is half equal to half moment of inertia mr square by 2 into angular velocity omega square minus omega naught square. Originally it was omega naught, finally it is omega. I replace theta just like I replace x, I replace it. So theta is minus omega naught plus omega by 2, because don't forget that at t equal to 0 this was clockwise spin, anti-clockwise spin, and this is clockwise spin. So minus omega naught plus omega by 2 into t is equal to, I just adjust this, I replace, I do this, so mr square by 2 by 4 into omega square minus omega naught square. Adjust it. So this gives me f, just play around with that, I get the step Fk into t is m by 2 into v plus v naught by 2. I call it equation 2. I divide equation 2 by equation 1. Divide 2 by 1, we get minus 1, because Fkt divided by minus Fkt gives me minus 1 equal to half, there you are, cancels. So half v plus v naught by 2 divided by v minus v naught. We solve this, we get v equal to v naught by 2. So interesting. Now certainly an average student will ask me, sir, why did you do the 3 methods? My answer is, I am doing this, my friend, I want you to understand the complete dynamics of rolling. So we have been able to use 3 methods, and all the 3 methods we get the same answer, v equal to v naught by 2. So very satisfying. But of course we do accept that the quickest method would be the first one, that is principle of conservation of angular momentum about an axis passing through P perpendicular to the plane of the disk. Now that is your choice, but then a good student, I am talking of students who are the IIT aspirants, the top medical, the NEET students, top medical students. The top medical students have physics conceptually as strong as that of IIT. I always have been saying that over the years. So if you learn it this way, my purpose was not to give you a solution. Solution, of course, I have done it. That is by conservation. I could have done it in 2 minutes. But by doing this, I have given you a very wide spectrum of the understanding of dynamics of rolling. I hope you have enjoyed this lecture, and please subscribe my channel so that you keep on getting such wonderful videos for your understanding of physics.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.